Albert Einstein once said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." Yet with every discovery, every breakthrough, the mystery only deepens. Like, look at your hand. What you're seeing isn't real. Not in the way you think it is. That solid flesh, those familiar fingers, they're mostly empty space. If an atom were as big as a football stadium, the nucleus would be just a tiny marble at the center. The electrons? Like dust particles zipping around way up in the stands. You are 99.9999999% nothing. But here's the thing that'll keep you awake tonight. You are the impossible thing. In a universe that shouldn't exist, made of matter that almost wasn't, governed by forces we can't explain, you somehow emerged from cosmic dust and began asking questions about your own existence. You are billions of years of stellar evolution packaged into a walking, talking mystery that can contemplate the mystery of itself. As you listen to these words, you're hurtling through space at 67,000 miles per hour. On a rock that's spinning around a nuclear furnace, that's racing through a galaxy. That's flying toward another galaxy. In an expanding universe that might be one of infinitely many universes. And somehow, you're not dizzy, but you should be. Because what I'm about to tell you will make you dizzy. It'll make you question everything you thought you knew about reality, about existence, about the very nature of what it means to be. You see, we've built a civilization on physics we don't understand. The smartphone in your pocket? It works because of quantum mechanics, a field so bizarre that the scientists who discovered it spent decades arguing about whether it could possibly be true. The GPS in your car? It only works because we account for Einstein's relativity. Time literally runs differently at different speeds and heights. Without these corrections, you'd miss your destination by miles. We've harnessed forces that make no sense. We've built technologies on foundations we can't explain. We've discovered a universe that seems designed to keep its deepest secrets from us. Everything you can see, every star, every planet, every galaxy, every single thing that light has ever touched amounts to less than 5% of what actually exists. The other 95%? It's invisible, untouchable, completely mysterious. We call it dark matter and dark energy, but honestly, we might as well call it magic. And that's just the beginning. Quantum mechanics tells us that particles can be in two places at once, that the act of looking at something changes what you're looking at, that particles separated by millions of miles can somehow know about each other instantly, faster than light itself. Einstein called it spooky action at a distance. He spent the last 30 years of his life trying to prove it was wrong. He failed. But here's the thing that haunts physicists. The deeper we dig, the stranger it gets. We've discovered that time isn't constant. It speeds up and slows down. That space isn't empty, it's seething with invisible energy. That the universe had a beginning, but we can't explain why it started, and we have no idea how it will end. We've found that consciousness might play a fundamental role in the structure of reality itself. That observation might literally create the world we observe. That you, yes, you, might be actively participating in the creation of the universe just by being aware of it. Now, most documentaries about science will try to comfort you. They'll tell you that we're making progress, that we're close to answering these questions, that science will eventually explain everything. I'm not going to lie to you. We are not much closer to understanding these mysteries today than we were 50 years ago. Despite building particle accelerators the size of cities, telescopes that can see to the edge of time, and computers more powerful than anything in human history, the universe keeps its secrets locked away. But here's why that's the most beautiful thing of all. These aren't just scientific problems waiting to be solved. They're invitations to wonder, opportunities to explore, reminders that we live in a cosmos so rich with mystery that conscious beings can spend their entire lives exploring it and barely scratch the surface. Welcome to the greatest mysteries of physics, a series where we'll journey together into the deepest puzzles of existence. In this first episode, we'll explore the dark universe in the first half of the video. Then, in the second half, we'll dive into the quantum paradox. So buckle up, the mystery begins now. Take a moment, look around you right now. The chair you're sitting in, the walls surrounding you, the very air you breathe, all of it, every single atom represents less than 5% of everything that exists. 5%? It's like walking into a room where 95% of the furniture is completely invisible. You'd bump into tables you can't see, trip over chairs that cast no shadow, feel the presence of something enormous that refuses to reveal itself. This isn't a thought experiment. This is the universe you live in every single day. Your body, your house, every star that's ever twinkled in the night sky, every galaxy astronomers have ever photographed, all of it combined is just the leftover scraps of creation. The universe is playing the ultimate magic trick, and for nearly a century, we've been the confused audience trying to figure out how 95% of reality managed to vanish in plain sight. The year was 1970. While most of the world was focused on moon landings and social revolutions, a quiet astronomer named Vera Rubin was about to discover something that would shatter our understanding of reality itself. Rubin wasn't looking for cosmic mysteries that night. She was simply trying to understand how galaxies spin, basic celestial mechanics, the kind of problem Newton might have tackled if he'd had a powerful telescope. She pointed her instruments at the Andromeda galaxy, our nearest galactic neighbour, expecting to confirm what every astronomer knew to be true. But the universe had other plans. What Rubin saw through her telescope that night should have been impossible. The outer stars of Andromeda were moving too fast, not just a little too fast, but catastrophically, impossibly fast. According to everything we knew about gravity and motion, those stars should have been flung into the cosmic void like water droplets flying off a spinning garden sprinkler. It's like sitting on a merry-go-round. Sit near the center, and you can hold on easily as it spins. But move toward the edge, and the faster it turns, the harder it becomes to stay on. Eventually the centrifugal force wins, and off you go, tumbling into the sand. That's exactly what should happen to stars on the outer edges of galaxies. Yet there they were, billions of stars, each one blazing with the light of our sun, somehow defying the fundamental laws of physics, spinning serenely in perfect formation as if held in place by an invisible hand. Rubin checked her calculation, then she checked them again. She pointed her telescope at another galaxy, then another. The same impossible pattern repeated itself, galaxy after galaxy, a cosmic conspiracy written across the heavens. Something was holding those stars in place, something with tremendous gravitational pull, something that contained 5 times more mass than all the visible matter in each galaxy combined. Something that was completely, utterly invisible. Rubin had discovered the first concrete evidence of what we now call dark matter. She didn't know it at the time, but she had just proven that we live in a universe where the things we can see are vastly outnumbered by things we cannot. But if dark matter was strange, what astronomers discovered 28 years later would be stranger. By 1998, two teams of astronomers were engaged in one of science's most ambitious projects, measuring the expansion of the universe itself. These weren't just any astronomers. These were the best in the world, using the most sophisticated telescopes ever built, studying the brightest explosions in cosmic history. They were looking at supernovae, the spectacular deaths of massive stars that shine brighter than entire galaxies for weeks at a time. These cosmic lighthouses are so consistently bright that astronomers call them standard candles. By measuring how bright they appear from Earth compared to how bright they actually are, scientists can calculate exactly how far away they are, and more importantly, how fast they're moving away from us. The plan was elegant in its simplicity. Einstein's equations predicted that the universe's expansion should be slowing down, like a ball thrown into the air that gradually loses speed as gravity pulls it back. By measuring how much the expansion had slowed over cosmic time, they could determine the ultimate fate of everything that exists. Would the universe expand forever, growing cold and dark as stars burned out one by one? Or would gravity eventually win, pulling everything back together in a cataclysmic big crunch? The answer lay hidden in the light of exploding stars billions of years old. What they found defied every prediction, violated every expectation, and launched a crisis in physics that continues to this day. The universe wasn't slowing down at all. It was speeding up. Not just speeding up, but accelerating at an ever-increasing rate, as if some invisible force was pushing space itself apart from the inside. The discovery was so unexpected, so fundamentally wrong according to everything we knew about gravity and cosmic evolution, that both teams spent months checking and rechecking their data, convinced they had made a mistake. They hadn't. The universe really was accelerating, driven by something that acts like anti-gravity on the largest scales imaginable, something that makes up 68% of everything that exists, something we can measure in its effects but cannot see, touch, or directly detect. We call it dark energy, though the name is almost laughably inadequate. It's not dark in any meaningful sense. It doesn't absorb light or cast shadows. It's not really energy as we typically understand the term. It's more like a property of space itself, a cosmic pressure that builds as the universe expands, pushing galaxies apart with ever-increasing force. Think of it this way. If you blow up a balloon, you expect the rubber to resist, making it harder to add more air as the balloon gets bigger. But imagine a balloon that becomes easier to inflate the larger it gets, as if the rubber itself was somehow generating more pressure from within. That's what dark energy does to the fabric of space and time. But here's what should keep you awake at night. We have absolutely no idea what it is. Let's take inventory of our universe, so it's time for the most humbling accounting in human history. Everything you've ever seen, touched, or experienced, every person who's ever lived, every planet we've discovered, every star that's ever lit up the night sky, represents 4.9% of the universe. Not quite 5%. We are the cosmic rounding error. 26.8% is dark matter. This invisible scaffolding holds galaxies together, bends light around massive clusters, and shapes the large-scale structure of the cosmos. We know it's there because we can see its gravitational effects, like watching an invisible person's footprints appear in snow. We've built detectors deep underground, launched sensitive instruments into space, and created elaborate theories to explain it. After 50 years of searching, we've never directly detected a single particle of dark matter. 68.3% is dark energy. This mysterious force is stretching space itself, accelerating the expansion of the universe and determining the ultimate fate of everything that exists. We discovered it barely 25 years ago, and we understand it even less than dark matter. It might be a property of empty space, a new kind of field that permeates reality, or evidence that our understanding of gravity itself is fundamentally flawed. Add it up. 26.8 plus 68.3 equals 95.1% of the universe that we cannot see, cannot touch, and do not understand. We have given these phenomena names, dark matter and dark energy, but calling something by a name is not the same as understanding what it is. These aren't just gaps in our knowledge, they're chasms that swallow our most fundamental assumptions about reality. Here's what makes this even more troubling: the precision of our ignorance. We can measure the amount of dark matter in the universe to incredible accuracy. We know exactly how much dark energy there is, how it affects cosmic expansion, and how it will shape the far future. We can create detailed computer simulations of cosmic evolution that match observations perfectly, as long as we include the right amounts of invisible stuff we don't understand. It's like being able to perfectly predict the weather while having no idea what air is made of. We've become masters of describing phenomena we cannot explain, experts in the behavior of things we cannot identify. But the mystery runs even deeper than this accounting might suggest. The search for dark matter has become one of the most expensive games of hide-and-seek in human history. And we're losing badly. Deep beneath the mountains of Italy, in abandoned gold mines turned into physics laboratories, scientists have built some of the most sensitive detectors ever created. These underground cathedrals of science are shielded from cosmic rays, isolated from vibrations, and cooled to temperatures colder than outer space. They wait in perfect stillness for the moment when a single particle of dark matter might crash into an atomic nucleus, releasing a tiny flash of energy that could revolutionize our understanding of the universe. The detectors have been running for decades. They've recorded cosmic ray impacts, radioactive decays, and every conceivable form of background noise. But dark matter particles? Zero. Not one. Not even a whisper of a signal that couldn't be explained by something else. Scientists have built particle accelerators the size of cities, smashing protons together at energies that recreate conditions from the first moments after the Big Bang. If dark matter particles can be created, these cosmic recreation centers should be manufacturing them by the billions. The experiments work perfectly, discovering new particles and confirming theoretical predictions with stunning precision. They just haven't found dark matter. Space telescopes scan the heavens, looking for the telltale signs of dark matter particles annihilating each other in the hearts of galaxies. They've mapped the cosmic web in exquisite detail, traced the invisible scaffolding that shapes the universe, and even created movies showing how dark matter flows through space over billions of years. But they've never caught dark matter in the act of being itself. This isn't a failure of technology or imagination. These experiments are so sensitive they can detect the movement of continents, the vibrations of passing trucks, even the gravitational effects of the moon's orbit. They're looking for something that should be everywhere. Remember, dark matter outweighs normal matter 5 to 1, yet finding nothing. Meanwhile, dark energy remains even more elusive. At least with dark matter, we have a conceptual framework. We know what to look for. Weakly interacting particles that clump together gravitationally. Dark energy doesn't even give us that courtesy. It might be a field, a particle, a property of space itself, or evidence that Einstein's equations break down on cosmic scales. The most honest thing we can say about dark energy is that it's the name we give to our ignorance about why the universe is accelerating. It's a placeholder, a cosmic IOU that we hope future discoveries will cache. But what if we're thinking about this all wrong? What if dark matter and dark energy don't actually exist? This isn't the ramblings of internet conspiracy theorists or scientific rebels without a cause. Some of the world's most respected physicists are seriously considering the possibility that we're not living in a universe dominated by invisible matter and mysterious energy. Instead, we might be living in a universe where our understanding of gravity itself is incomplete. The theory is called modified Newtonian dynamics, or MOND, and it suggests something radical. Maybe gravity doesn't work the way we think it does on the largest scales. Newton's law of gravity and Einstein's general relativity work perfectly in our solar system, but perhaps they break down when dealing with the vast distances between stars in galaxies. Under MOND, there's no need for dark matter to explain why galaxies spin the way they do. The stars aren't being held in place by invisible particles. Gravity itself becomes stronger over galactic distances, naturally accounting for the extra gravitational pull Vera Rubin observed. It's an elegant solution that eliminates the need for 26% of the universe to be made of particles we've never detected, but it comes with its own problems. MOND struggles to explain other observations that dark matter handles easily, like the way light bends around galaxy clusters or the patterns we see in the cosmic microwave background radiation. And MOND doesn't address dark energy at all. Even if we can eliminate dark matter by modifying gravity, we still need to explain why the universe's expansion is accelerating. Other theories go even further. Some suggest we're living in a universe with extra dimensions that we can't perceive directly, where gravity can leak between these hidden dimensions, creating effects we misinterpret as dark matter and dark energy. Others propose that space and time themselves are emergent properties of something more fundamental, that reality is like a hologram projected from information encoded on a distant surface. These aren't just abstract mathematical exercises. Each alternative theory makes testable predictions, and as our instruments become more sensitive, we are slowly but surely narrowing down the possibilities. But here's what's truly unsettling about all these alternatives. They suggest that our fundamental understanding of reality, the very foundations upon which modern physics is built, might be wrong in ways we're only beginning to comprehend. Let me paint you a picture of the universe as it actually exists, not as our earthbound intuition imagines it. Imagine you could see dark matter the way you see ordinary matter. Suddenly the night sky would blaze with invisible architecture. Vast filaments of dark matter stretch between galaxies like cosmic spider webs, forming a network so large that our entire galaxy is just a tiny ornament hanging on one of its strands. These dark matter highways shape everything. Galaxies form where the highways intersect, like cities built at the crossroads of ancient trade routes. The beautiful spiral arms of galaxies, they're just the visible foam riding on massive waves of invisible matter that dwarf them in every dimension. If you could somehow remove all the normal matter from the universe, every star, every planet, every atom of gas floating in the void, the dark matter would still be there, holding its shape, maintaining the cosmic architecture that makes galaxies possible in the first place. We are the decoration, not the foundation. And dark energy? It's even stranger. It's not concentrated in particular places like dark matter. It's everywhere, uniformly distributed throughout space, a property of the vacuum itself. Every cubic centimetre of empty space contains dark energy. And as the universe expands, there's more empty space, which means more dark energy, which means faster expansion, which creates even more empty space. It's a runaway process that will eventually tear the universe apart. In the far future, trillions of years from now, dark energy will overcome not just gravity, but every other force that holds matter together. Galaxies will be torn apart, solar systems will be shredded, and eventually even atoms themselves will be stretched beyond their breaking point. The universe began with a Big Bang, and will end with what cosmologists call the Big Rip, the moment when dark energy finally wins its battle against every other force in nature. But we're getting ahead of ourselves. Right now, in our current cosmic epoch, dark matter and dark energy exist in a delicate balance that makes complex structures like galaxies, stars, and life itself possible. Change the amount of either one by even a small percentage, and the universe becomes a very different place, either collapsing too quickly for stars to form, or expanding so fast that matter never gets a chance to clump together. This precise balance raises its own troubling questions. Questions that cut to the heart of why anything exists at all. We've been talking about dark matter and dark energy as if they're separate mysteries. But what if they're connected in ways we don't yet understand? What if the invisible universe operates according to rules that are completely alien to our everyday experience? Consider this. Normal matter, the stuff you're made of, interacts with itself in countless ways. Atoms can combine into molecules. Molecules can form complex structures, and those structures can organize themselves into everything from crystals to living cells. The electromagnetic force allows matter to stick together, heat up, cool down, and emit light. But dark matter appears to be much more aloof. It interacts gravitationally with normal matter and with itself, but that seems to be about it. It doesn't emit light, absorb light, or combine into complex structures the way normal matter does. It's like a parallel universe of particles that exist in the same space we do, but follow their own separate rules. Some physicists have proposed that dark matter might have its own rich internal structure. Dark atoms made of dark protons and dark electrons, perhaps even dark chemistry and dark biology. There could be entire civilizations made of dark matter existing alongside us, completely unaware of our existence, just as we're unaware of theirs. It sounds like science fiction, but the mathematics works out. There's no fundamental reason why dark matter has to be simple. The only constraint is that it can't interact with light, which means any dark matter civilization would be invisible to us, and we would be invisible to them. Dark energy raises even stranger possibilities. If it's truly a property of space itself, then it's not really a thing so much as a characteristic of nothingness. Empty space, it turns out, isn't empty at all. It's seething with dark energy that pushes against gravity and drives cosmic expansion. But here's where it gets really weird. The amount of dark energy seems to be perfectly calibrated to allow galaxies and stars to form. Too much. And the universe would expand so fast that matter could never clump together. Too little. And gravity would win, causing everything to collapse back into a big crunch long before stars had time to forge the heavy elements necessary for planets and life. This precise calibration is one of the deepest mysteries in all of physics. It's as if the universe was fine-tuned to produce exactly the right conditions for complexity and consciousness to emerge. A cosmic Goldilocks zone written into the fundamental constants of nature. But that raises an uncomfortable question. Fine-tuned by what? Or by whom? Every time you look up at the stars and the universe is lying to you, those pinpoints of light scattered across the darkness, they represent less than 1% of what's actually there. The rest, the vast majority of reality, is invisible, undetectable to your eyes, no matter how clear the night or how far you are from city lights. It's not just that dark matter and dark energy are invisible. It's that their invisibility is so complete, so absolute, that it took us until the 1970s to realize they existed at all. For thousands of years, humans have been staring at a universe that was mostly hidden from view, constructing cosmologies and philosophies based on the tiniest visible fraction of what's actually out there. Imagine if you tried to understand a city by only looking at the streetlights. You'd see these isolated points of illumination scattered across the darkness, and you might even notice patterns in their arrangement. But you'd have no idea about the buildings, the roads, the infrastructure that connects them all together. That's been humanity's relationship with the cosmos for most of our history. Even now, with all our sophisticated instruments and theoretical frameworks, we're not much better off. We can map the dark matter, measure the dark energy, and predict their effects with stunning precision. But we still don't know what they actually are. This isn't like other mysteries in physics, where we're missing a few pieces of the puzzle. This is like discovering that 95% of the puzzle pieces were never in the box to begin with. We've been working with what we thought was a complete picture, only to discover that we've barely begun to glimpse the true scope of reality. And here's what should really keep you awake at night. If we were wrong about something this fundamental, this pervasive, what else might we be missing? What other invisible components of reality are we oblivious to, simply because we lack the tools or the concepts to detect them? The dark universe isn't just a collection of unsolved problems. It's a profound humbling of human knowledge. It's the universe's way of reminding us that reality is far stranger, far more complex, and far more mysterious than our earthbound experience could ever prepare us for. But the story gets stranger still, because dark matter and dark energy are just the beginning of physics' crisis of understanding. We've mapped the invisible architecture of the cosmos, measured the acceleration of space itself, and discovered that everything we thought we knew about the universe represents less than 5% of what actually exists. But all of these discoveries lead to one question that cuts deeper than any other. Why does the universe work this way? Why does dark matter exist in exactly the right proportions to allow galaxies to form? Why does dark energy have precisely the value needed to prevent cosmic collapse while still permitting stars and planets to condense from primordial gas clouds? Why is the balance between these invisible forces so exquisitely calibrated that complex structures, and ultimately consciousness itself, can emerge from cosmic chaos? If dark matter was slightly more abundant, galaxies would have formed too early, when the universe was too hot and turbulent for stars to ignite properly. If it were less abundant, galaxies would never have formed at all. Matter would remain forever dispersed in a thin, cold fog. If dark energy were stronger, the universe would have torn itself apart before the first stars could form. If it were weaker, everything would have collapsed back into a cosmic crunch within a few million years of the Big Bang. The parameters aren't just approximately right. They're right to a degree that seems almost impossibly precise. It's as if someone carefully adjusted the dials of reality to create a universe capable of producing complexity, beauty, and conscious beings who could contemplate their own existence. But here's the thing. No one adjusted those dials. As far as we know, the universe just is the way it is, for no reason we can fathom. The values of dark matter and dark energy appear to be arbitrary constants of nature, like the mass of an electron or the speed of light, fundamental parameters that simply define the reality we happen to inhabit. This leads to one of two unsettling conclusions. Either we live in an extraordinarily unlikely universe that just happened to roll the cosmic dice exactly right, or there are countless other universes with different parameters, and we exist in this one simply because it's the only type where conscious beings can evolve to ask these questions in the first place. Both possibilities challenge our deepest assumptions about existence, purpose, and our place in the grand scheme of things. But the crisis in physics goes deeper than dark matter and dark energy. These invisible components of the universe are just symptoms of a more fundamental problem, one that strikes at the heart of how we understand reality itself. The dark universe has revealed that 95% of reality is invisible to us, operating according to rules we don't understand, balanced with a precision that seems almost miraculous. We've discovered that we live in a cosmos dominated by forces and substances that remain completely mysterious despite decades of searching. But what if the problem isn't that we can't find the answers to these cosmic mysteries? What if the problem is that we're asking the wrong questions altogether? What if the very fabric of space and time, the stage upon which the dark universe performs its invisible dance, is itself nothing like what we imagine it to be? What if reality at its most fundamental level operates according to principles so alien to our everyday experience? That dark matter and dark energy are just the tip of an iceberg of cosmic strangeness. To understand why the universe hides so much of itself from us, we need to journey deeper into the quantum realm, where the familiar rules of reality break down completely, and where the very act of observation changes what we observe. We need to explore a domain where particles can be in multiple places at once, where the future can influence the past, and where consciousness itself might play a fundamental role in determining what becomes real. Welcome to the quantum paradox, where the impossible happens billions of times per second, and where the deepest mystery isn't what we can't see. It's why anything becomes definite enough to see at all. Close your eyes for a moment. Now open them. In that brief instant of darkness, something extraordinary happened. Billions of quantum events unfolded in your retina, each one defying everything your common sense tells you about reality. Particles of light called photons struck molecules in your eye, and those molecules existed in multiple states simultaneously until the moment of impact. They were quite literally everywhere and nowhere at once. This isn't poetry. This isn't mysticism. This is quantum mechanics, the most successful theory in the history of science, and also the most disturbing. It's the reason your smartphone works, why the sun shines, and why your DNA doesn't unravel. Yet it describes a reality so alien that even its pioneers refuse to believe it. Welcome to the quantum world, where the impossible happens every nanosecond, and where the very act of looking at something changes what you see. The story begins in 1900, when physicist Max Planck faced a problem that should have been simple. Why does a heated piece of metal glow the way it does? Classical physics predicted that hot objects should emit infinite amounts of ultraviolet light, something called the ultraviolet catastrophe. But Planck discovered something shocking. Energy doesn't flow continuously like water from a faucet. Instead, it comes in tiny, discrete packets, quanta, like drops from a leaky tap. Planck thought this was just a mathematical trick, a convenient fiction to make the numbers work. He had no idea he'd just cracked open Pandora's box. 5 years later, Einstein, yes, that Einstein, took Planck's idea seriously. He proposed that light itself comes in packets, which we now call photons. Picture this. The warm sunlight on your face isn't a smooth wave of energy. It's a machine gun burst of billions of tiny bullets of light, each one carrying a precise amount of energy. But here's where it gets strange. Einstein showed that these photons behave like particles when they hit things, but like waves when they travel through space. It's as if a baseball could spread out like a ripple on a pond while flying through the air, then suddenly become solid again when it hits the catcher's mitt. This wave-particle duality would become the first crack in our understanding of reality. But it was just the beginning. In the 1920s, scientists like Werner Heisenberg and Erwin Schrödinger began to realize that this wasn't just about light, it was about everything. Every electron, every atom, every fundamental particle in existence was playing by these impossible rules. And that's when physics stepped through the looking glass, into a world where Alice's Wonderland seems perfectly sensible by comparison. Erwin Schrödinger was horrified by what quantum mechanics was telling him about reality. To show just how absurd it all was, he devised a thought experiment that has haunted physicists for nearly a century. Imagine a box containing a cat, a Geiger counter, a radioactive atom, a hammer, and a flask of poison gas. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggers the hammer to smash the flask, and the cat dies. If it doesn't decay, the cat lives. Now, according to quantum mechanics, until you open the box and observe the system, the radioactive atom exists in what's called a superposition. It's both decayed and not decayed simultaneously. Which means, following the logic to its absurd conclusion, that the cat is both alive and dead at the same time. Schrödinger thought this was ridiculous. He believed it proved that quantum mechanics couldn't be the whole story. But here's the twist that would have made Schrödinger's hair stand on end. We now know that quantum superposition is real. We can create it, manipulate it, and use it. In laboratories around the world, scientists routinely create what are called quantum bits or qubits, systems that exist in multiple states simultaneously. Unlike a normal computer bit that must be either 0 or 1, a qubit can be 0, 1, or both at the same time. It's like having a coin that's simultaneously heads, tails, and spinning in the air. Google's quantum computer, Sycamore, uses 70 qubits to perform calculations that would take classical computers thousands of years. It's literally harnessing the power of parallel realities to solve problems. Each qubit exists in multiple states, allowing the computer to explore countless solutions simultaneously. But this raises the most unsettling question of all. If quantum superposition works for atoms and photons and qubits, why don't we see it in everyday life? Why isn't everything around us existing in multiple states at once? The answer leads us into an even deeper mystery, one that strikes at the very heart of what we mean by reality. Here's perhaps the most disturbing discovery in the history of science. The universe seems to behave differently when someone is watching. In quantum mechanics, particles don't have definite properties until they're observed. It's not that we don't know where an electron is, it's that the electron doesn't know where it is. It exists as a cloud of probabilities, a ghostly presence spread across space. Only when we measure it does it suddenly collapse into a definite location. This isn't a limitation of our instruments. The act of observation literally changes reality. Consider the famous double-slit experiment. Fire electrons one at a time through two parallel slits toward a screen. If electrons were simply particles, they'd create two stripes on the screen, one behind each slit. But they don't. Instead, they create an interference pattern with multiple stripes, as if each electron went through both slits simultaneously and interfered with itself. Now place a detector at one of the slits to see which path each electron takes. Suddenly, the interference pattern disappears. The electrons start behaving like ordinary particles, creating just two stripes. It's as if they know they're being watched and change their behavior accordingly. This isn't just true for electrons. Photons, atoms, even large molecules containing over 2,000 atoms have been shown to exhibit this bizarre behavior. The boundary between the quantum world and the classical world we experience isn't about size, it's about observation. But what counts as observation? Does it require consciousness? A human observer? Or does any interaction with the environment count? We still don't know. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in shaping reality. Others propose that the universe splits into parallel branches every time a quantum measurement occurs. The most unnerving possibility of all? That reality is fundamentally observer-dependent. That the universe only becomes real when conscious beings like us observe it, which means you're not just living in reality, you're actively creating it with every glance, every measurement, every conscious observation. This brings us to the phenomenon that Einstein called spooky action at a distance, a connection between particles so instantaneous and profound that it seems to mock our understanding of space and time itself. Einstein hated quantum entanglement. He spent the last decades of his life trying to prove it impossible, calling it spookhafte Fernwirkung, spooky action at a distance. He was convinced that no influence could travel faster than light, and quantum entanglement seemed to violate this fundamental principle. He was wrong. Imagine you have a pair of quantum particles created together. Let's call them Alice and Bob. No matter how far apart you separate them, across the room, across the galaxy, across the universe, they remain mysteriously connected. Measure a property of Alice, and you instantly know the corresponding property of Bob, even though neither particle had that definite property before you measured it. It's not that Alice sends a signal to Bob. The connection is more profound than that. It's as if Alice and Bob are two parts of a single quantum system, sharing what Einstein mockingly called a ghostly connection that transcends space and time. In 1964, physicist John Bell proved that this connection is real and measurable. Since then, experiment after experiment has confirmed what Einstein couldn't accept. Quantum entanglement is a fundamental feature of reality. Today, we're not just studying quantum entanglement, we're using it. Quantum cryptography relies on entangled particles to create unbreakable codes. If anyone tries to intercept the message, the entanglement is broken, and both sender and receiver know immediately that their communication has been compromised. Scientists have successfully entangled particles across hundreds of kilometers, creating quantum networks that could one day link quantum computers around the globe. China has launched satellites that create entangled photons in space, demonstrating quantum communication on a planetary scale. But here's what keeps physicists awake at night. Quantum entanglement suggests that the universe is far more interconnected than we ever imagined. If particles separated by vast distances can instantly affect each other, what does this mean for our understanding of space, time, and causality? Some interpretations suggest that entangled particles aren't really separate objects at all. They're aspects of a single, undivided quantum reality. If true, then the sense of separation we experience in everyday life might be an illusion. At the deepest level, everything in the universe might be connected in ways that transcend our ordinary understanding of physics. This interconnectedness leads us to one of the most profound questions in science. What role does consciousness play in the quantum world? Here's a question that will make your head spin. What if consciousness isn't produced by the brain, but is instead a fundamental feature of the universe, like mass or electric charge? This isn't New Age mysticism. It's a serious hypothesis proposed by some of the world's leading physicists and neuroscientists. The question arose because of the measurement problem we discussed earlier. If observation collapses quantum wave functions, and if consciousness is required for observation, then consciousness might play a fundamental role in shaping reality. Nobel laureate Eugene Wigner proposed that consciousness is the missing ingredient in quantum mechanics. In his view, quantum systems remain in superposition until observed by a conscious being. The wave function doesn't collapse when it interacts with a measuring device. It collapses when a conscious observer becomes aware of the measurement result. This leads to scenarios so bizarre they sound like science fiction. Wigner's friend, locked in a laboratory, observes a quantum system and sees it collapse into a definite state. But from Wigner's perspective, outside the lab, both his friend and the quantum system remain in superposition until Wigner himself observes the result. In other words, from Wigner's viewpoint, his friend exists in a superposition of having seen different measurement outcomes. Recent experiments have actually tested variations of Wigner's thought experiment with results that challenge our basic assumptions about objective reality. Different observers can apparently witness different incompatible events, a finding that suggests reality might be fundamentally observer-dependent. But consciousness might play an even deeper role in quantum mechanics. Physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that consciousness arises from quantum processes in microtubules within brain cells. According to their controversial theory, our thoughts and experiences are quantum computations. Our brains are literally quantum computers made of biological tissue. If true, this could explain some of the mysteries surrounding consciousness. Why do we have subjective experiences rather than just processing information unconsciously? Perhaps because consciousness is the universe's way of collapsing quantum superpositions, the mechanism by which possibility becomes actuality. The implications are staggering, and every conscious thought might be collapsing quantum wave functions. Every moment of awareness might be creating reality rather than simply observing it. You wouldn't just be a passive observer of the universe, you'd be an active participant in its creation. But this raises an even more fundamental question. If consciousness can influence quantum systems, what happens when we try to understand consciousness itself using quantum mechanics? The human brain contains approximately 86 billion neurons, each connected to thousands of others through synapses that operate partly through quantum mechanical processes. Every thought you're having right now involves quantum events. Photons being absorbed by molecules in your retina, electrons tunneling across synaptic gaps, quantum fluctuations in the microtubules of your neurons. Yet somehow this quantum machinery produces something that seems utterly different from quantum mechanics: consciousness. You have a unified, continuous sense of self. You experience colors, sounds, emotions, and thoughts as definite, concrete realities, not as probability clouds or superposition states. This is the hard problem of consciousness, and quantum mechanics makes it even harder. If your brain operates according to quantum principles, why don't you experience quantum superposition? Why don't you think multiple contradictory thoughts simultaneously? Why does your consciousness seem classical in a quantum world? Some researchers suggest that consciousness emerges when quantum decoherence occurs, when quantum systems interact with their environment and lose their quantum properties. In this view, consciousness is the boundary between the quantum and classical worlds, the process by which definite reality emerges from quantum possibility. Others propose that consciousness might involve quantum effects that persist despite decoherence. MIT's Max Tegmark has calculated that quantum coherence in the brain should be destroyed almost instantly by the warm, noisy environment of living tissue. Yet some researchers argue that biological systems have evolved ways to protect and exploit quantum effects. Recent studies have found evidence of quantum coherence in photosynthesis, in bird navigation, and even in the sense of smell. Life, it seems, is quantum in ways we're only beginning to understand. If evolution has found ways to harness quantum mechanics in other biological processes, why not in consciousness? The most radical possibility is that consciousness might be necessary for quantum mechanics to work at all. In the participatory universe, proposed by physicist John Wheeler, observers don't just observe reality, they participate in its creation. Consciousness might be the universe's way of actualizing itself, of choosing which of infinite possibilities becomes real. If this is true, then every conscious being is literally helping to create the universe through the act of observation. You're not separate from the cosmos. You're one of the ways the cosmos observes and defines itself. But this brings us face to face with the deepest puzzle of all. If consciousness can influence quantum systems, and if consciousness itself emerges from quantum processes, we have a strange loop, consciousness creating the reality from which consciousness emerges. While philosophers debate the meaning of quantum mechanics, engineers are busy building machines that exploit its strangest properties. Quantum computers don't just use quantum mechanics, they are quantum mechanics, embodied in circuits of superconducting loops and trapped ions. A classical computer processes information in bits that are either 0 or 1. A quantum computer uses qubits that can be 0, 1 or both simultaneously. This isn't just twice as powerful, it's exponentially more powerful. While a classical computer with 300 bits can represent 1 of 2 to the power of 300 possible states, a quantum computer with 300 qubits can exist in all 2 to the power of 300 states simultaneously. To understand the magnitude of this difference, consider that 2 to the power of 300 is approximately 10 to the power of 90, a number larger than the estimated number of atoms in the observable universe. A quantum computer with just 300 qubits could, in principle, perform more calculations simultaneously than there are atoms in existence. Google's quantum computer achieved quantum supremacy in 2019, performing a specific calculation in 200 seconds that would take the world's most powerful classical computer 10,000 years. IBM's quantum computer can factor large numbers using Shor's algorithm, threatening the cryptographic systems that secure our digital world. But quantum computers are fragile. The quantum states they rely on are destroyed by any interaction with the environment, a process called decoherence. Quantum computers must be isolated from vibrations, electromagnetic fields, and even cosmic rays. They operate at temperatures colder than deep space, in environments more isolated than the most pristine laboratory. This fragility isn't a bug, it's a feature. It reveals something profound about the nature of quantum mechanics. Quantum effects are usually hidden from us because they're destroyed by interaction with the environment. Classical reality emerges when quantum systems become entangled with their surroundings. Yet somehow, quantum computers have found ways to manipulate and preserve quantum states long enough to perform calculations. They're like windows into the quantum world, allowing us to directly observe and control the strange physics that underlies all reality. And they're just the beginning. Quantum sensors can detect gravitational waves by measuring distortions smaller than 1/10,000th the width of a proton. Quantum clocks are so precise they could detect the gravitational time dilation caused by raising them a single centimeter. Quantum communication networks could create absolutely secure communication channels protected by the laws of physics themselves. But perhaps the most profound impact of quantum technology will be on our understanding of consciousness itself. If consciousness involves quantum processes, then quantum computers might help us understand how mind emerges from matter. What if every quantum measurement doesn't just collapse a wave function? What if it splits the entire universe into parallel branches? This is the radical proposal of the many worlds interpretation, first suggested by physicist Hugh Everett III in 1957. According to this theory, every time a quantum system is in superposition, the universe branches into multiple parallel realities, one for each possible outcome. Consider Schrödinger's cat again. In the many worlds interpretation, the universe splits when the radioactive atom reaches the moment of potential decay. In one branch, the atom decays, the detector triggers, and the cat dies. In another branch, the atom doesn't decay, and the cat lives. Both outcomes are equally real, they just exist in separate branches of reality. This isn't science fiction. It's a serious interpretation of quantum mechanics, endorsed by many leading physicists. Max Tegmark at MIT estimates that quantum branching occurs at a rate of 10 to the power of 100 times per second. Every quantum event in every atom in your body is potentially splitting the universe into parallel versions of itself. Think about the implications. Every decision you've ever made, every quantum coin flip in your brain has created parallel versions of yourself. Right now, there are countless copies of you reading these words, each experiencing slightly different quantum outcomes. Some versions of you decided to skip this documentary. Others watched it at different times. In some branches, different historical events unfolded because key quantum measurements had different outcomes. The many worlds interpretation solves many problems in quantum mechanics. It eliminates the measurement problem. Wave functions never collapse because all possibilities remain real in different branches. It removes the need for consciousness to play a special role in physics. It makes quantum mechanics fully deterministic at the universal level, even though it appears random from our limited perspective within a single branch. But it creates new mysteries. If parallel worlds exist, why don't we experience them? How do the branches split? And what determines which branch we find ourselves in? Are the other versions of you equally real, equally conscious? Some physicists propose that consciousness might be the mechanism that selects which branch of reality we experience. In this view, your awareness isn't just observing reality, it's choosing which reality to observe from among infinite alternatives. Others suggest that all branches are equally real, but we can only experience one at a time because consciousness cannot split along with the universe. You have countless parallel selves, but each is aware only of their own branch of the cosmic tree. The most unsettling possibility is that the branching never stops. Every quantum event creates new parallel worlds, leading to an ever-growing multiverse of infinite complexity. If true, then everything that can happen does happen, somewhere in the vast space of parallel realities. We've journeyed deep into the quantum realm, where particles exist in multiple states simultaneously, where observation changes reality, and where consciousness might play a fundamental role in shaping the universe. We've explored the possibility that every quantum measurement splits reality into parallel branches, creating an infinite multiverse of alternative histories. But here's what makes quantum mechanics so profoundly unsettling: it works. Every prediction it makes, no matter how bizarre, has been confirmed by experiment. Quantum computers harness superposition and entanglement to solve impossible problems. Quantum cryptography uses the laws of physics themselves to create unbreakable codes. Quantum sensors achieve precision that seemed impossible just decades ago. Yet despite its unprecedented success, quantum mechanics remains deeply mysterious. We can calculate what will happen, but we still don't understand why it happens. We can harness quantum effects, but we can't explain why reality behaves in such a counterintuitive way. The strangest part of all, you are a quantum being. Every atom in your body, every photon that enters your eyes, every electron that fires across your synapses operates according to quantum mechanical principles. The thoughts you're having right now emerge from quantum processes in your brain. Your consciousness itself might be a quantum phenomenon, the universe's way of observing and actualizing itself. Perhaps the most profound realization is this: quantum mechanics has shown us that reality is far stranger and more interconnected than we ever imagined. The boundaries between observer and observed, between mind and matter, between possible and actual, are far more fluid than classical physics suggested. But if quantum mechanics governs everything from atoms to thoughts, why doesn't gravity, the force that shapes galaxies and bends spacetime itself, obey quantum rules? This incompatibility between quantum mechanics and Einstein's general relativity represents one of the deepest problems in physics. It's a mystery that could hold the key to understanding the nature of reality itself. And that's where our journey takes us next, into the broken marriage between the two greatest theories in physics and the quest to unite them in a single, elegant description of everything that exists. But our exploration is far from over. In the next episode, we'll dive into the broken marriage between quantum mechanics and general relativity, and chase the signals from nowhere, enigmas that could reveal new dimensions or truths we've yet to fathom. Stay curious, for the greatest mysteries of physics await.